So let's continue. So what I hope I've convinced you in the previous part is that at the points where the function obtains its maximum and its minimum on our surface, the directional derivative of the function in the directions that are in the tangent plane to the surface must all be zero. Now, how do we find what the directional derivative in the direction of a vector is? So if we take some unit vector, I'll put a hat on it because it's a unit vector, and I'll underline it. In fact, I might underline that also to show that it's a vector. So if we have some vector, and it'll be ux, uy, uz, then if we want to know what the directional derivative in the direction of that is, we just dot product this gradient vector with this. So what I am now saying is that I want it to be the case that if I dot product this vector with any of the vectors in the tangent plane to my surface, I want it to be the case that I get 0. Now think about the dot product. When does the dot product equal 0? It equals 0 when the two vectors that you are dot producting are perpendicular. So if this has to dot product with all the vectors in a plane to give 0, that means that it is perpendicular to that plane. So at this point here, if I try and actually draw the tangent plane, and this is a dangerous quest because it's probably going to look very stupid. So this is supposed to try and represent that tangent plane to the unit sphere at the point 1, 0, 0. It doesn't do it very well, but this can represent it. This plane is going to be perpendicular to the vector, the gradient vector of our function. And of course you can see that that's true. The tangent plane is parallel to the yz plane at that point, and that is of course orthogonal to this vector which is 2, 0, 0, which points in the x direction. What we now know is that if a point on this surface is going to be a maximum or a minimum, or indeed a stationary point more generally, then the tangent plane at that point must be orthogonal, perpendicular to the gradient vector of our function. And that's why these 2 points are the only stationary points for this function on this unit sphere surface, because they're the only points where the tangent plane is going to be orthogonal to the gradient vector. Remember, the gradient vector is a constant vector that points in the x direction with magnitude 2 everywhere. Can you see any other points on this sphere where the tangent plane is going to be orthogonal to that? No, it's only where the tangent plane is going to be this parallel to the yz plane, and the only 2 points with that are this point here, 1, 0, 0, and this point over here, minus 1, 0, 0. So we're making progress. This is the idea of the Lagrange multipliers technique, that we can work out the stationary points for our function, and the maximum and the minimum will be among those stationary points. Of course, in this case it's very simple. There are only 2 stationary points, and one is the maximum and one is the minimum. In more general examples you might have far more stationary points, and then you have to go through the different ones to find out which one is the maximum and the minimum. But this is the idea, that stationary points, we can find them by finding points where the tangent plane is orthogonal to the gradient vector of the function that we're trying to find the stationary points of over that surface. Now it gets even better than that, because of course the tangent planes are going to be perpendicular to the normal vectors of the surface. So if instead we think about normal vectors to the surface rather than tangent planes, then all we actually need to do is find points on the surface where the normal vectors are parallel or anti-parallel to the gradient vector. So of course in this case the normal vector is going to be pointing in this direction, and in this case it's going to be pointing in this direction. So here it's going to be parallel to the gradient vector 2, 0, 0, and here it's going to be anti-parallel to the gradient vector 2, 0, 0. So that is the idea of Lagrange multipliers, that if you want to maximize or minimize a function over a surface, then you start by finding its stationary points over that surface, and to do that you find the normal vectors to the surface, and you find where are the normal vectors parallel or anti-parallel to the gradient vectors of your function. Those are the points on the surface where the directional derivative in any direction that is in the tangent plane to the surface at that point is going to be 0. Those are going to be the stationary points on your surface. Now, of course, if we had a more complicated problem, you would have to think more carefully. Let me explain what I mean. So let's use an analogy from single variable calculus. Say I gave you the job of maximizing and minimizing the value of this function over this interval. So this is the interval a, b, and I want you to maximize and minimize, find the maximum and find the minimum value of the function over that interval. Well, if you were naive, you might just differentiate it and find the stationary points, and you'd find those 2 points, but of course that is not the right answer. The maximum is actually at the point B, and the minimum is at the point A. We don't have to worry about that in the case of this sphere, because the sphere doesn't have these edges. Any maximum and minimum on this sphere is going to be a stationary point. It's going to have derivative 0. The problem that arose here is because you have these edges, you have these opportunities where you can have maxima and a maximum and a minimum where the derivative isn't 0. So this wouldn't be a maximum, for instance, if you extended the boundary a little bit. If you extended it to here, then suddenly this would no longer be a maximum. And similarly, this would no longer be a minimum if you extended the boundary here and the function continued on downwards. So be aware of that, that if, for instance, your problem is instead, let's draw a new space here. So if instead the problem is, here is a surface like this, and we're just going to take a small portion of this surface, so I don't want to take the surface all the way to infinity, instead I'll just cut a bit out of it, so maybe this bit here, then you can see that this has edges in the way that the sphere doesn't have edges. So it has the opportunity for the same thing that arose here to happen, that you could have a maximum and a minimum where the function isn't actually a stationary point, or that point isn't actually a stationary point for the function on the surface. So be aware of that, that the sphere is a beautiful example for doing Lagrange multipliers because it doesn't have this problem of having these edges where you can have a maximum or a minimum that isn't a stationary point. So enough talking about the general ideas then. Let's actually demonstrate how you do this, and we'll start by doing it for this function 2x plus 1, and then we'll do it for this more complex function, and we'll do it over this surface x squared plus y squared plus z squared is equal to 1. So we want to find points on our surface here where the normal vector is parallel or anti-parallel to the gradient vector for our function. Now we've already done the first part, which is find the gradient vector for our function. So the next thing we need to do is find normal vectors to our surface. Now, if our surface looked more like this, then we might have it written as z as a function of x and y. So we might have it written as z being an explicit function of x and y. In that case, if you wanted to find normal vectors to your surface, what you would probably do is find the tangent vector at each point in the x direction, find the tangent vector in the y direction, and you do that using the partial derivative, so just to demonstrate that. So if we wanted the tangent vector in the x direction, we'd have 1, and then we'd be going none in the direction of y, and then we'd have dz dx, the partial derivative of z with respect to x, so that would be the tangent vector in the x direction, and in the y direction you'd go 0 in the x direction, 1 in the y direction, and then the ratio between z and y, so dz dy, partial of z with respect to y. So you'd get these two vectors, which are the tangent vectors in the x and the y direction, and then you'd cross product them, and that would give you the normal vector to the surface. So that's one way you could do it. In the case of our sphere, there is a much nicer way to do it. Obviously, the sphere isn't written in terms of an explicit function. Now, we could change it into an explicit function. We could write it as z is equal to the square root of 1 minus x squared minus y squared. Of course, that gets rid of half of the sphere. It gets rid of the bottom half, so you then have to also have the function z is equal to minus of that. So we could do it in that way. that's a mess. We're not going to do it like that. Instead, what we're going to do is something really clever. So our surface, we're going to actually think of it as being a level surface for a function. So for instance, if I create a new function, which we'll call g, which is a real valued function of r cubed, again, r3, x squared, and it's equal to, g is equal to x squared plus y squared plus z squared, then this surface, the unit surface, is a level surface of this function. It's the level surface for g is equal to 1. Now, if I was to find the gradient vector of this function, which I can do, it's a real valued function of r3, so I can find its gradient vector, I know that the gradient vector is always going to be perpendicular, normal, to the level surfaces. So in particular, all of the gradient vectors for the points on this unit sphere, they're all going to be normal to the unit sphere. So that will give me the normal vectors to my surface, the unit sphere. So that's what I'm going to do here. So instead I can just find this gradient vector, and I apologize that I'm going all over the place. So nabla g is equal to 2x, 2y, 2z. So just the partial with respect to x, the partial with respect to y, and the partial with respect to z. And you can see that that quite clearly nicely works. So if I plug in, for instance, 1, 0, 0, this point here, that gives me 2, 0, 0. Now, note it's not a unit vector, it's just a normal vector, but it doesn't matter that it's not a unit vector. After all I'm looking for is for this vector to be parallel to this vector. I don't care about the size difference between the two. So it doesn't matter that it's not a normal vector. Not a unit vector. So here you can see that it will give 2, 0, 0, which is normal to the surface here. If we go up to this point here, which is 0, 0, 1, we'll get 0, 0, 2, which obviously points straight upwards. So everywhere it's going to be giving a vector that's perpendicular to the tangent plane and is pointing straight outwards. It's not pointing inwards, it's the normal vector pointing outwards that it's given us. Because, of course, it points in the direction of increasing g. So g is increasing outwards, not inwards. That's a property of the gradient vector, that it always points in the direction that the function goes up in. Now, so I've got my normal vector to the surface everywhere. Of course, I only want to be putting in x, y, and z values that are on my surface. Otherwise, if I take an x, y, and z value that's not on the surface, then it's giving me the gradient vector of this function g elsewhere. So the only bit that is useful to me is if x, y, and z are subject to this constraint, i.e. they're actually on my surface. So if I pick my x, y, and z such that they're actually on the surface and plug them into this, it will give me the normal vector. So now what I want to do is find when is this parallel to this on my surface. So the 4 things that I've really got 4 equations here. Firstly, I've got the x squared plus y squared plus z squared must equal 1. So the point must be on my surface. And then I've got the 3 equations that come out of this vector equation, which is nabla f needs to equal, and then this new thing, lambda, which is the Lagrange multiplier, after which the technique is named, times nabla g. And this lambda, by the way, this is just some real number. It could be positive, it could be negative, it could even be 0. And what this is capturing is the fact that this one needs to be parallel or anti-parallel to this one, which is the normal vector to our surface. So if they are parallel to one another, then this will be a positive constant. If they are anti-parallel to one another, then this will be a negative constant, which will flip the vector in the other direction. If the function actually has a full-on stationary point on your surface, so a point where the gradient vector itself becomes 0 on your surface, then that is more than just a stationary point on the surface. It's a stationary point in the entirety of R3, but that is still going to be a stationary point on the surface. So in that case, lambda would be able to be 0 to give you this gradient vector of 0 for the entire function. So if we write down what this is in the case of our example, so our nabla f is the vector 2, 0, 0, then we've got that this must equal lambda times, and then our nabla g is 2x, 2y, 2z. And this is why I said really we've got 4 equations here, and now we've got 4 variables now that we've got the Lagrange multiplier that is also a real variable and can take any real value. So our 4 equations that we need to solve are x squared plus y squared plus z squared is equal to 1, and then we've got 2 is equal to 2 lambda x, we've got 0 is equal to 2 lambda y, and we've got 0 is equal to 2 lambda z. Those are the 4 equations. So now this is what we've got from the Lagrange multiplier technique. We've got that if we can find a point, values x, y, and z, and a value lambda that satisfy these 4 equations, then that will be a point on our surface that will be a stationary point for the function and may well be the maximum and minimum. And indeed, in this example, we're only going to get these 2 solutions, which are 1, 0, 0 and minus 1, 0, 0, and those will be the maximum and the minimum, respectively. So let's solve this system of equations then now. So, where should we begin? From this one, we get that lambda x must equal 1. From these two, so we know now that lambda cannot equal 0, because if lambda was equal to 0, it wouldn't work. This equation wouldn't work. So that means that we can divide through by lambda here. In fact, we can cancel the 2 lambda, and we can get the conclusion that y and z both must equal 0. Then we can plug that information back into equation number 1 here to get that x squared must equal 1, i.e. that x must equal plus or minus 1. Those are the 2 possibilities, and then we just need to make sure that for both of those that they can satisfy this. So if we put in x is equal to plus 1, then lambda equals plus 1, and there we have a solution. So one solution is 1, 0, 0 with lambda equal to plus 1. That's one solution to our system of 4 equations. And then the other solution is minus 1, 0, 0, and in that case, to make this equation work, lambda is going to have to equal negative 1. And of course, that corresponds to the fact that for this point, the gradient vector is parallel to the normal vector. So here, if you put in 1, 0, 0, you get 2, 0, 0, so they're the exact same vector. So the multiplier that you need, the Lagrange multiplier you need, is just 1. And in this case, if you plug in minus 1 here, you get the gradient vector pointing in the anti-parallel direction. It's pointing in this direction here. So you'll get minus 2, 0, 0, which is, of course, anti-parallel to this. So the Lagrange multiplier needs to be negative 1. So there we have the 2 solutions. Those are the only 2 points on our sphere where the function is stationary. And of course, if we want to work out which one's the maximum and which one's the minimum, we just plug them into the actual function. So plugging 1, 0, 0 in here, you get 3. Plugging minus 1, 0, 0 in here, you get minus 1. So clearly, this one is the maximum, and this one is the minimum. So that's an example of using this Lagrange multiplier technique to solve that problem that was extremely simple, that we knew the answer just from intuition. We'll have a break here, and in the next video we'll use this same technique to solve this more complicated problem where we're trying to find the stationary points of this function on our unit sphere.